You're watching Invention Chronicles, exploring the greatest ideas ever imagined. Every second, our sun releases more energy than humanity has ever produced. But what's really happening inside its mysterious core? Dive with me. As I pass the glowing surface, the noise of violent plasma fades into a deeper rhythm, gravity's heartbeat. At the center, the pressure is crushing, more than 200 billion times Earth's atmosphere. Temperatures climb to about 15 million degrees Celsius. Here, hydrogen nuclei, protons, are forced so close that the strong nuclear force takes over. They fuse. This is the proton-proton chain. Two protons collide. One transforms into a neutron, releasing a positron and a ghostly neutrino that escapes almost instantly. The new deuterium nucleus grabs another proton to make helium-3. Two helium-3 nuclei then merge into helium-4, spitting out two spare protons to start the cycle again. In each step, a tiny bit of mass goes missing and reappears as energy, E equals mc squared. Tiny, but relentless. Trillions of times per second. The energy doesn't rush out as light right away. Photons born in the core bounce a chaotic pinball path, scattering for tens of thousands of years before they reach space. By the time sunlight kisses your skin, it's the echo of an ancient fusion event. Fusion is nature's most powerful invention, the engine of every star we see at night. It forged the heavier elements in stellar furnaces, supernovae, seeding the universe, planets, oceans, life, our weather, our seasons. The food we grow, all of it powered by a star doing simple arithmetic with hydrogen. And it's more than a cosmic curiosity. Fusion is a blueprint for an energy future we're trying to build here on Earth. Imagine power with no carbon emissions, no long-lived high-level waste. Fuel sourced from seawater, fuel sourced from lithium. That's the promise that keeps scientists and engineers up late. To mimic a star, you need star conditions. One path uses magnetic bottles, tokamaks, stellarators. They confine plasma hotter than the sun's core, so hot that atoms split into a charged soup. In that state, hydrogen isotopes like deuterium, tritium can fuse, releasing immense energy. Projects like ITER, now rising in southern France, are building the most ambitious magnetic confinement reactor in history. The goal? Produce 500 megawatts of fusion power from about 50 megawatts of input, a tenfold energy gain in the plasma. Not electricity yet, but proof that net energy fusion in a reactor-scale device is possible. There are other approaches too. Inertial confinement uses lasers to compress tiny fuel pellets in microbursts of star-like conditions. New startups are trying pulsed magnets and compact tokamaks, fusion driven by particle beams. Each is a different road toward the same horizon. The challenges are real. Materials must survive brutal neutron bombardment. We have to produce and recycle tritium safely. Plasma has moods, instabilities that can push back against confinement. But every year, diagnostics improve, algorithms get smarter, and magnets get stronger. The engineering gap narrows. Here's the perspective I love. Fusion is not just about electricity. It's a lesson in patience and scale. The sun took billions of years to shape a stable fusion engine. We're a century into learning how to hold a star in a ring of magnets for just a few steady seconds, and then minutes. Progress isn't flashy, but it compounds. Stand back with me for a final look. The sun hums on, fusing hydrogen into helium, turning mass into light, turning time into life. It warms our planet and writes our story in photons. The sun reminds me, the greatest inventions are born in nature itself. Thank you for watching. Stay curious and keep exploring the world of invention and discovery. Don't forget to like and subscribe for more discoveries on Invention Chronicles.